Okay, we're ready to go. This time we made sure to do a sound check so we know that the audio is on, unlike last time when we had that little mix-up. All right, so at the end of class last time, and I assume that, I guess I'll ask if there's any questions. I assume no one has done started doing the homework for Thursday at this point in time, right?
Actually did.
Oh, you actually did?
This time I started this early.
Oh, whoa, I'm impressed. I'm impressed. So are there any questions about the homework that's due 2 days from now? All right. So at the end of class last time, we were talking about Theorem 9.7. So let's take a look at Theorem 9.7 on the slide here. It's the distributivity of and over for all, right? Conjunction over universal.
I actually do have a question.
Oh, okay.
Sorry. It's for the, because in the homework we proved like 9.6, I think.
Yeah, I asked you to prove 9.6, yes?
Yeah, on 9.6, I used trading, but with an empty range.
Yeah.
Is it okay?
No, hold.
If the range is.
No, hold on. I want to make sure that you said you used with an empty range. Now you understand that in 9.6 on the right hand side, this is not the empty range.
Okay, range true, my bad.
Okay. So yeah, you're right. That's range true. Which is different from the empty range. Empty range is empty range is when the range is false.
And then I used trading like 9.3a.
Okay.
And which has like it does, but that's not the one I use.
But well, whatever.
Say if I have equivales, like I have a quantification equivales a quantification, and the range is the same on both. Could I? Because I don't know how the textual substitution works, but could I have true on both if I'm using?
Well, with any of these theorems, you can. They work in general. For example,
like I use 9.5. That's what it is. I use 9.5.
Okay, so
instead of R, of R was true.
Yeah, you can use 9.5 with R being true. Of course, yeah.
So how do you do textual substitution? Like
No. That's not text. Well, it's 9.5 with R replaced by true.
Oh, because normally the textual substitution is just like variable. What do we do? Like,
oh yeah, I see.
Expression replaced by true.
Oh, that's right. You have a good point there. Because normally when we do textual substitution,
it makes sense. It works.
Well, it works for an arbitrary R, therefore it works for R being the expression true. So that's legal.
I don't do you don't do any kind of substitution.
Well, it's legal to do it's legal to use 9.5 with R being true, which is what your question was, right? Yeah, that's good. Good question. So.
Sorry for the sidetrack.
No problem. All right. So now we were doing 9.7. We're starting, and we said what 9.7 says is that this equivales this, but only if what? Only if the range is everywhere false, because it says if the range is everywhere false, then this. Are you with me?
No.
Is everybody following me here?
Isn't it if it's not everywhere false?
Sorry. You're right. If the range is not, my mistake. Thanks for catching that. If the range is not.
What if it was everywhere false? It's not everywhere.
You can't do it.
Then you can't do it.
Obviously you can't do it, but like why?
Well, I'll show you. I think when we do the proof, you'll see why that has to be the case. You'll see. All right. So now what we want to do is prove this theorem, right? Now, and guess what? I'm noticing now that in your proofs that a lot of people are really liking this. Whenever we have to prove an implication, a lot of people are liking this, assuming the conjuncts of the antecedent, right? So let's do that. Okay, so let's prove by Prove by assuming, well, there's only one, there's only one, right? By assuming the antecedent. All right, but now before we start this, do you understand that anytime we use a proof by assuming the conjuncts of the antecedent, what do we have to do? We have to start with the what? The consequent and get it to what? True. So so what we have to do is we have to start with this whole thing and get it to true. Are you with me? But we're going to use two proof techniques in one. Because we know that if you have an equivalence, one way to do it is to start with the whole thing and get it to true, but we also know that it's possible to do what? Start with one side and get it to the other. So now does everybody understand that we're combining two proof techniques? Okay? So prove by assuming, and then use a second technique. Use a second technique, proving equivalence. Proving equivalence by starting with one side. Now, so is everybody comfortable with this?
Sure.
All right. And which side do you think we should start with? It won't matter, but let's start with this side, I think. Yeah, because we want to pull, what we want to do with this, we want to get it and we want to be able to pull this out, right? So, here's the proof. So, what was that side? For all x,
Range R.
range R, body. Well, does anybody have any ideas?
Maybe trading.
Well,
Which one of seven?
what are we trying to do here? We're trying to get this. What are we trying to get with this P? We're trying to get it out here, right? And so we have this, and this and this. What do you think?
How about we throw in a Demorgan on it?
Well, I don't see any knots floating around.
Well, we don't need one.
Well, the Demorgan has to do with knot, right?
Well, we can pull a knot out of all of them.
But why do we want to pull a knot out?
So we can make it an OR and then use 9.6.
And use what?
9.6.
We need to move on that again.
Yeah, but how do you pull a knot out of a for all?
Couldn't we do it just for P and Q?
You see what I'm saying? Because actually, we haven't gotten that far. We haven't gotten later on.
That's not what he's talking about.
Well,
Just for the body.
Just for the body.
just for the body. Yeah, but then what would you have? You'd have not parentheses, not P or not Q. Then how do you do that not? I don't think that's.
Yeah, just kinda
You see what I'm saying?
just a little ugly.
Nice try.
Close but no cigar.
Close but no cigar. Close only counts in horseshoes and atom bombs. Well, come on, you guys. Come on, how are we going to get this out of here? How are we going to get this?
Literally no idea.
All right, I will give you.
Is it on that page?
No, I will give you a hint.
No, don't do that.
I know, it's kind of like admitting defeat, isn't it?
Yeah.
I mean, don't you hate it to have to stop and ask directions when you're lost?
Oh, absolutely. Golden.
It's, golden rule. Oh, wow. But if we had a golden rule, then that would change that to P or Q, equivalence, blah, blah, blah. And we don't have any theorems that deal with equivalence in the body.
We have trading 9.4C, 9.4D, 9.3B, 9.3C.
Well, all right. I'm going to have to give you a hint. Let's try some of these generalized ones.
I was looking at that.
Because you understand that just because we're starting to deal with,
I don't have any conjuncts in the body though.
well, I know, but what is star in these generalized ones?
Yeah, it's anything.
It's anything. And what operation are we dealing with here? And, because it's a for all.
Oh, do 815.
Ha! Ha! All right. So, great, Ben. So, equals by, Ben, 8.15, which is,
That's quite smart.
that is pretty smart.
So,
By 8 point, I need a, could you hand me that eraser? Thank you. Yeah, that was a good call. 8.15, I still can't write a 5. 8.15, boom. And because what does 8.15 say?
it says, you can
It
do
would
one star
be-
another, and the body is with a star.
Yeah, so the star is, it's for all x, range r, body p, and then that star in the middle is like and, right? And there's our and. Okay, so what is this? By 8.15, what is it?
How do you say the upside down A?
For all.
Okay, for all x,
For all x,
range R,
range r,
body P.
body p, and
for all x, range R, body Q.
r, body q.
What is 9.7? Does it satisfy those proviso?
Well, notice that 8.15 has provided p and q are Boolean.
And R is finite.
No, or r is finite. Or r is finite. And p and q are now, are we? Actually, that's a good point.
X doesn't compare P.
Are we agreed that p and q are Boolean?
Because of the and.
Because of the and, p and q are Boolean. So yeah, that was a good check. Okay. 8.15, p and q are Boolean.
What
That's
do you mean by R is finite?
and not infinite, like dot dot dot, you know, forever. Okay, so p and q are Boolean. So let's put that in our note. So our proviso holds. Okay, ooh, and now we have this part of our thing, right? So now what? Now what? That was a very good call. Now, which one are we trying to prove? 9.7.
Use 9.6.
Ah, we got another good call. By 9.6. And what does 9.6 tell us? And what, do we have a proviso for 9.6?
Not as good as X and P.
And is that the same as we have here?
Yeah.
Okay. So, because not occurs, oops. X in P. Okay, so what does that give us?
That gives you your conjunct.
So what's over here? You're doing it on for this one?
Yeah.
Okay, so what does that give us?
Definitely that one.
So what?
Parentheses P or open parentheses for all X.
For all X.
Range, not a
Range, how do we say this?
body.
No, wait, range true. We say range true.
Range true.
Is everybody good?
Yeah.
For all X, range true, body what?
Not a.
Body not R. Is everybody clear on this? And then this stays, and then we'll close the print here, right? And then this and for all X, range R, body Q.
Range split.
Whoa, wait. And what now what technique are we using? What are we doing? We're
Assuming not R. It's here.
yeah, so
Oh, it's an or.
But we don't have a not the whole thing, do we?
Oh, it's just or.
Oh, you're assuming none.
We need not for all blah blah blah, not
Yeah. So we are assuming not this. So therefore what, so therefore what is this?
false.
Yeah.
Okay.
By what?
Okay, so here what we're
know
doing is
that, but by what?
assume,
Because we're assuming the conjunct.
because we're assuming the conjunct. I mean,
So because.
we're
not
we're
false.
assuming the conjunct is true, so therefore not the conjunct is false, right?
Do we have to quote like
Wait, so doesn't that mean that anything that isn't the conjunct could be false?
definition of false?
No, it means the negation of the negation of each conjunct must be false. Okay,
Or
so.
the lack thereof.
Or the lack there, I don't know. I'd have to think about that. Okay, so our assumption is that, wait, what was our assumption?
Not all that.
Our assumption is not for all x range true, body not R. Right? Are we good? So therefore, because if this is our assumption, therefore this next step is what? Is P or false. And for all x range R, body Q. Are we good?
0 or
And 0 of or
identity of or.
Identities.
or identity. Oh, yeah, not 0.
Right.
Identity of or.
That was a mistake.
Identity of disjunction gives us what?
What we want.
P and for all x range R, body Q, bam. Did everybody follow every step? We good? See, these you just keep on trucking. You know, it's just now that we know these proof techniques, and we go back and substitute equals for equals. Okay, everything works. All right, now your homework for next time is 9.6, 9.8. Let's take a look. So your homework for tomorrow is next time 9.6, 9.8. Ooh, look at 9.8. For all x range R body true, that equivalence true.
Dumb.
Yeah, but you can't do this.
It's hard.
It's hard to do because it's obvious that it's the true, but you can't like expand it out because R is general. You can't say true and true and true and true is true. Because you can't, there's nothing that says expand it out. So somehow you got to get that. Where in the heck does true come from?
Exactly. True, so it creates truer. Yeah.
More true? Truer? So anyway, so you'll have to puzzle on that one. So put that in your list of to-dos. And 9.9 is another one for the homework. For all x range R, body P equivalence Q, that implies for all x range R body P equivalence for all x range R body Q. So that's another one for you to puzzle over. 9.9. 9.11, this is one of those ones where we're starting a new topic and you're gonna have a bunch of proofs to do. So you got a lot of work for next time. 9.11 is another one you're gonna do for your homework. Body weakening strengthening. Ooh, what does this say?
We can weaken and strengthen.
This says that if it's the case that for all x range R body P and Q, then that implies for all x range R body P. But, you can't just do this in one step saying that P and Q implies P. Because that's what this is saying that you can do. You would be assuming what you're trying to do, to prove. Do you see what I mean? Yeah, now this is everybody clear on the problem with 9 point? Here, let me say, don't,
You can't use weakening.
you cannot use, here, yeah, let me show you an incorrect proof. So don't be tempted to do this. Okay, so incorrect proof. Incorrect proof of 9.11. It's not just this. See, you might be tempted to say for all x range R, body P and Q, implies by, now what was the strengthening?
3.76B.
7.6 something.
It is B.
3.76B, which is P and
It's the exact same thing as this one.
Q
You have to add
implies
76B in it.
implies P. Yeah, here. And then, see, this is for all X range R, body P. Okay? What I'm saying is that this is wrong. That's wrong. Huh?
How's that wrong?
No, yeah,
Oh.
it's a sticky situation.
Yeah, we need to make sure and get this cleared up. Look, what you can do is this.
The whole thing when you-
Yeah, look, here's what you can do. If you say, if you have, what you can use 3.76B for is if you have sum for all X, blah, 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 and for all X,
And you just do 815.
blah, 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 like this, then it is the case that you can use 3.76B to say that this implies one of them. Are you with me?
Yeah, you would just do 815
Okay.
first.
Well,
Same stuff.
are you with me?
I'm with you.
Totally.
Does everybody see what I'm saying? It is legal to use, it is legal if you have this and outside of the parens, because then this is the little p and this is the little q, and that does imply just one of them.
You split them up.
But the thing of it is that if it's inside here, you would be assuming what you're trying to prove here. Do you see what I mean? I mean, you'd be, so. Does everybody get that concept of how you have to have that pulled out? Okay, so 9.11 is one of them. And then the next one is 9.13. Now 9.13 is, for the homework for next time, is instantiation. Now, I used to just assign 9.13 with a few hints, and 9.13 is very subtle. There's a subtle problem involved with 9.13. And so to help you to do 9.13, I have a little worksheet for you. It's supplementary exercise S.3. Okay, so I'll pass that around.
1 point rule.
Okay, so on the web page there is, you can download this if you want, but I printed them out for you. It's supplementary exercise S.3 is to take you through the steps of proving 9.13 instantiation. And like I say in the note here, the thing of it is that are there any provisos in 9.13? There's no provisos, right? So you're going to somehow you're going to have to use 8.14 on this. Let's take a look at 8.14. So the 8.14 is the only previous axiom or theorem that we have that has this textual substitution in it. So you know you're going to have to do 8.14. The problem is 8.14 has this proviso. Are you with me? 8.14 has this proviso, but the one that we're trying to prove, 9.13, oops, 9.13 does not have any proviso. This works in all cases, no proviso. So it's a little subtle about how you take care of that, and so what I've given you here are the hints with the steps to fill in to show you how you get rid of that, you know, how you can use 8.14 with the proviso in such a way that this doesn't have the proviso. So it's a little subtle. So anyway, did everybody get one? All right. Okay. So now actually let's think about that for a minute. Now look, this is a really interesting one. This is kind of a crucial one, 9.13. Do you see what 9.13 is saying? Do you understand why this is a reasonable, I mean, a reasonable
For
theorem?
all x.
Because if P is true, what this is saying is that if P is true for all the possible values of x,
And P is also true for
then it is true for what?
everything with x replaced by e.
Well, then it is true for,
Yeah.
yeah, for one of them. Are you with me? What this is saying is that if it's true for all possible x's, then it is true for one of them. Right? Because this is P with x replaced by any expression.
Yeah.
You see? So do you see why that follows? It's because if you have something that is universally true in all cases, then it has to be true for whatever you put for whatever you put for one. If it's true for all of them, it has to be true for a you know,
That's common sense.
that's what instantiation. What does it mean to instantiate something? It means like bring it into existence. You know, bring an instance of it. So if it's true for all of the cases, it's true for that instance. It's true for this particular instance. If it's true for all, it's true. And obviously, the implication doesn't go the other way. If it's true for just this instant, that doesn't mean it's true for all of them, right? So the implication is that. Does everybody see how that works?
Yeah.
So what's interesting then is that whenever we get to existential quantification, then we will have these same kinds of things, but they'll be different. Universal and existential are kind of like mirrors of each other. Okay? So 9.13 is also a homework problem, but that's S.3, and you can do that with the help of the worksheet. All right. I think you're with me. Okay. Now, the next one that I would like to talk about is 9.16. I'll give you a note about 9.16. See if we can get some insight into what it means.
What?
What?
You're not kidding, of course.
Well, what this says, what 9.16 says is that P is a theorem if and only if, for all x range true, P is a theorem.
Sure.
And in order to kind of like understand how this works, I want to give you a few examples with some free variables. All right. So let's do a note on 9.16. As it turns out, this is also kind of a crucial one, and because it relates predicate calculus with propositional calculus. Okay.
Do we have to prove this one?
Do we have to prove this one? No, actually, I'm going to show you. I'll show you a proof of this. It's in the book, but I'll show it. But I want to give you an example. Okay, so first of all, a quantified expression without free variables is either true or false, independent of any state. Let's write that down. A quantified expression without free variables is either true or false, independent of any state. Independent of any state. Okay? So that's our first observation. And let me give you a couple of examples. Now, I'm going to use an exists. There exists an I, range 4 less than or equal to I less than 8, body I equals 6. Now, what is there exists? What's the operation for there? It's or. No, you think you told me that recently.
On the tab.
Yeah. Okay.
I didn't tell you that.
Some of you told me that. Okay, so this is or. So what does this mean? So what are the possible values of I in this range? What are the possible values of I? 4, 5, 6, 7. Okay? And so what is this? This is 4 equals 6.
Oh, right.
What is it? It's 4 equals 6 what? Or 5 equals or, okay? So tell me, now are there any, here, is this I bound or free? Is this I bound or free? Are there any free variables? So do you agree that this thing is either true or false, independent of any state?
Yep.
And which is it, true or false? It's true. Does everybody see what we're saying here?
One true.
Are you with me on this? Okay. Now how about this? For all I, 4 less than or equal to I less than 8, body I equals 6.
False.
What this is saying is that 4 equals 6 and 5 equals 6 and 6 equals 6 and 7, right? But this is what?
False.
This is false,
How
right?
do you have a state in there anyway?
Well, you can't, there is no state because there's no free variables.
It's in
Okay.
It could be in any state then if there is no state.
Well, hold on. So, this is not, okay, so these expressions, I'm just making a point. These expressions are not like, say, P or Q, which may be true or false depending on the what? Depending on the state, you know. What's the definition of state?
list of variables and
And their values. So what state would this be true in? Give me a state.
the true and false.
Yeah, P is true, Q is false. Okay, give me an example of when this is false, 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 right? Okay, so these expressions are not like P or Q, which may be true or false, which may be true or false, depending on the state. All right? Is everybody with me on that? So everybody understands the difference between something like this and something like this, because this doesn't have any free variables. Okay, now tell me this. How about this? There exists an I range 4 less than or equal to I less than 8, body I equals M.
Well, it depends what state M is.
Because why? Because M is a what?
Free variable.
M is a free variable. A free variable, right? So the truth depends on the state, right? Give me an example of M for which it's true.
5,
Give me an example for which it's false.
Negative 53.
Yep.
but only that one.
You had to get all of them.
Does everybody see that? The truth depends on the state. Okay, now watch this. Now, with that in mind, let me give you an example of 9.16. Okay? So, check this out. So here is an example of 9.16. Suppose you have this. An example. Because, check this out. Because, now what do you know about this? P or Q equivales Q or P.
Because it's symmetrical.
Wait, does this look familiar? P or Q equivales Q or P. Does this look familiar? This is a theorem. Are you with me? P is a theorem, right? Because this is a theorem. Because this is a theorem, so is, now watch this, so is for all P range true, because that's a range true, right? For all P range true, P or Q equivales Q or P. Now tell me, what do we,
We're allowed to leave the Q.
what, well, yeah, tell me, you know, what do we know about this and this? What kind of a variable is this? This is bound. And this one is what? Free. Okay? But still, this is a theorem. It's saying this, it's what that is saying is that this is a theorem.
Any state, it's true.
Yeah. Right. This whole thing is a function of one variable, right?
Yeah. Even if
Because it's a function of, because Q, if you expand this out, then Q. Because what is this, what is this for, if we were to expand this out, what would we have? If we were, what are the possible values of P?
True or false?
True or false? So for all, kind of like, so what is this saying? This is saying for all P. So what is this is saying is that true or Q equivals Q or true, and then what? And what?
true or Q.
No, and what? False or Q equivals Q or false. That's a theorem.
Still true. Q equals Q.
That is a theorem. Because this is a theorem, so is this.
Yeah.
So no matter what we plug into it, any theorem that we've studied so far.
Any theorem that we've studied so far.
It's like, yeah.
This is called, actually, whenever we, actually, you know what we're saying here? And, you know, and in fact, even this, how about this? For all PQ reigns true. P or Q equivals Q or P.
Oh yeah.
See? I mean, this is also a theorem. Okay? Because, you know, you know, this,
What if we say for all Z? P or Q.
So they're all free?
yeah, I mean, this is also a theorem. This is saying that this is a theorem.
Sure.
Right? Okay?
That's the interesting question.
So now, this is something, 9.16 is called, see, look, you guys, this actually connects, propositional calculus with proof by truth tables. Do you remember how we would always say that, I guarantee, remember I gave you a challenge, I said, I guarantee you, if you do the truth table for every single one of these theorems, it will always be true, 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 true. Right? And I guarantee that that's the case. Well, here's how I knew that. This is how I knew that. Because what this says is that for each one of those theorems, for all x, P is a theorem.
What if X is an NP? Then it's okay?
Still, yeah. Okay? So 9.16 is called implicit universal quantification. 9.16 is called, quote, implicit universal quantification. Now, what does implicit mean?
It exists.
No. You say, oh, well, that's as opposed to, what's the opposite of implicit? Explicit. The opposite of what's explicit mean? It's no, not lots of cuss words. No. Oh, yeah. Slightly different meaning of explicit. Explicit means visible, it's shown, right? Implicit means hidden. Yeah, well, it's implied, but it's hidden. So, with those theorems, we implicitly are saying, all those theorems that we did in propositional calculus, we are saying that those are implicitly universally quantified. In other words, we are claiming that those are true for all P's and Q's and R's. Are you with me? That's what was implied by it being a theorem. This actually proves it. Now, here's our book has a nice little slide here. There's a nice little section. Yeah. And this is a demonstration. 9.16 is actually a meta-theorem because it says, he is saying, is a theorem. And we don't have a way to manipulate is a theorem. Are you with me? So, yeah, we don't, so this is a meta-theorem. Now tell me the definition of a meta-theorem. It's a theorem about a theorem. Okay? So 9.16 is called meta-theorem, and here is the reproduction of the page from the book where he shows how it works. So let's see if so here he says P is a theorem if and only if for all x range true P is a theorem. So here's the proof. He says the proof is by mutual implication. Now remember what mutual implication says? What was the mutual implication? What was equivales. How did that work? What was mutual? Do you remember
Q
mutual?
plus Q and
Something about
Q plus
equival.
P.
Yeah.
Equivales.
Which one? Yeah. Which one was that?
No idea, doesn't matter.
Well, let me find it here. Did I pass it?
There you go.
Mutual implication, 3.80, right? 3.80 says P implies Q and Q implies P equivales Q. Oh, that was one of our proof techniques, actually, that we never did because I said, yeah, we hardly ever do it, and I couldn't think of an example.
No,
Well, now here's an example. How do you show that P equivales Q? Well, you do it in two steps. First, you should prove that P implies Q, and then you show that Q implies P, right? So here, if we go back to here, so we're going to, it says P is a theorem if and only if for all x range true, P is a theorem. So it's proof by mutual implication. So first, let's assume that P is a theorem, all right? And we will show that for all x range P is a theorem, right? So if P is a theorem, then there must be a proof of it that transforms P to true. Are you with me?
sure.
So P, hint 1, hint 2, true, right? So P has to equivalent true, right? Okay. There is a proof, okay. But then what happens is Leibniz, which is 8.12, oh wait.
You mean 312.
Oh, was it 3? Wait.
412.
Wait.
It says 812.
It's 812. No, it's 812. Yeah. Leibniz is the step. Leibniz is how we substitute equals for equals. Are you with me? That's our proof. That's a proof rule. That's not a theorem or an axiom. That's a proof rule. Okay, so Leibniz allows us to turn this into a proof of for all x range true body P. And because basically what you would do is you would start with for all x range true body P, and then you would use the same hint that you used in the proof up there, you would just use that for that part, right? For the P. And eventually you would get to for all x range true body true. But at that point, you can invoke what? 9.8, which I think, didn't we just say that this is one of the ones that you were going to prove?
Yeah, exactly.
But that means true, right? So therefore that is a theorem, right? Because we got it to equivalent true.
Cool.
Are you with me?
Sick.
And then the other way around says, the right-hand side, let's do the other way around. Now let's assume that for all x range true body P is a theorem, right? Well, look, now then we can use instantiation, which is 9.13. Remember what instantiation was?
That's the one with the.
That's the one, if it's true for all of them, it's true for one of them. So let's just, x replaced by x. See, here, let's do 9.13. Here, instantiation. Look, here, instantiation. For all x range true body P, that implies P with x replaced by P. But look, if we just do P with x replaced by x, what? That's P. Didn't you do that? Wasn't that one of the steps that you did in the proof for me on the exam, where it's P with x replaced by x, property of textual substitution? That's just P, because if everywhere there's an x replaced by x, that's
It
P.
was R, but yes.
But it's the same thing, right? Okay. So are you with me?
Yeah.
So therefore, we have shown 9.16 metatheorem. Yeah? All right. Well, that's all pretty heavy-duty stuff. Okay. And I believe that completes our presentation of for all. Now, the next thing that we're going to look at then, we still have a few minutes, and since you're all still so enthusiastically with me here, the next thing that we will introduce is existential quantification. You don't want to exist? Oh my goodness. Do we have existential questions here? We have
Apparently.
I want to know what kind of
Quantification.
I want to know the first person that was like, I just want to do numbers. And everyone else is like, we're farming.
All right, you guys. Here is existential quantification. Now look. Do you remember how in propositional calculus, yeah, we had the golden rule. And what did we do first? The first thing that did we do and first, or did we do or?
Or
Yeah, I think yeah, you're right. I think we did or. We had all these theorems for or, and then boom, we had the golden rule which connected or and then we derived all those other corresponding theorems from that, and we just needed that one to connect it, and then we could get all those other properties. Well, look, you guys, we have all these properties of and. We have this trading, we have these different versions of trading, we have more versions of trading, we have universal double trading, we have an axiom here, and then we have all of this stuff, range weakening, body weakening, strengthening, that you're going to prove, all of this stuff. P is a theorem, all this stuff, right? And now we have, one axiom. It's kind of like our golden rule, right? This is our golden rule for predicate calculus. And what it does is it relates exists and for all. And with that, it's called the Generalized Demorgan theorem. Then we can prove all of these other ones, corresponding properties of existential. And let's take a look at what it says.
it's something we've seen before.
It said, well,
It was our assumption in the proof we did at the beginning of class.
oh. Not for all. Oh, you're right. It is. Nice call. It says there exists in X, range R, body P, equivals. It's not the case that for all X, range R, body not P. Okay? So put that in your pipe and smoke it. And we'll talk about it in more detail on Thursday. All right, good deal. You don't think we should cut that one? Okay.